Hello everyone, my name is Isabelle. I'm a PhD student at the University of Neuchâtel, and I am here today to talk to you about secure task-based programming with OmpSs and SGX, which is a collaborative work between my university and some colleagues at the Barcelona Supercomputing Center and the Polytechnic University of Catalonia. The goal of our work is to support asynchronous task parallelism and hardware heterogeneity under secure mechanisms. Our approach relies on the combination of OmpSs programming model for the data dependency management and Intel SGX for the privacy requirements. SGX is an application isolation technology which we propose to be used by those tasks which have security as part of their requirements. In this case, the programmer has to adapt these tasks to the expected SGX format. This is needed because the fundamental protection provided by SGX is that enclave secrets can only be accessed by code that is inside the enclave itself. And the only way to execute that code is through enclave's interface functions that have already been defined. Because of time constraints, I cannot go into details of how these modifications are exactly performed, but because the SGX SDK abstracts a lot of the low-level details, this adaptation basically consists of defining some C or C++ functions describing the secure tasks and linking them with the SGX interface via files that loosely resembles a C-style header with function prototypes. Once the necessary tasks have been adapted to support SGX execution, the code is compiled by the SGX compiler, and the secure functions can be integrated to the main application, which is already annotated with calls to Nano's runtime, responsible for taking care of the asynchronous and parallel execution of tasks, as well as the management of data dependencies among those tasks. The main application code is compiled with Mercurium compiler and is then finally ready for utilization. In order to evaluate our approach, we have also performed some microbenchmarks using these three different applications to measure performance and energy overhead of supporting secure tasks. Besides of that, we also evaluate the overhead correlations by varying the number of threads, the scheduling algorithm being used, the task's input size, and the application's graph size. Our main finding, as it can be observed in these graphs, was that added overhead can vary a lot depending on the application and its configurations. And this is why it's very important for the user to well understand the application's requirements. If you're interested in more details, this application source code and their experimental results are available on this GitHub repository, so you can refer to it later on. With that, I conclude my presentation and thank you for your attention.